Hello there and welcome to Calm Chronicles. Tonight we are setting out across the widest stage history has ever known, the open ocean. Long before satellites traced coastlines and engines erased distance, human beings pushed wooden hulls into unknown water and trusted wind, stars, and memory to carry them forward. Every ocean expedition was a wager with the planet itself. Survival depended on patience, observation, and an ability to listen to a world that does not speak in words. This is a story of curiosity that refused to stay on shore, of ships that vanished and ships that returned changed forever, of ideas carried across waves, and of knowledge gathered slowly, one sounding line at a time. Ocean expeditions shaped maps, empires, science, and even the way we understand time and distance. They connected continents, revealed hidden depths, and reminded humanity how small it could feel beneath an endless horizon. But for now, let your shoulders soften and your breathing slow. Let the day loosen its grip and allow your thoughts to follow the tide outward as we explore the long and remarkable history of ocean expeditions. Let's begin. Ocean expeditions mapped most of the world before any airplane existed. For most of human history, the fastest way to learn what lay beyond the horizon was to sail straight into it. Mariners traced coastlines by watching the color of water, the shape of clouds, and the smell of land carried on wind. They sketched bays and shoals, then returned years later to correct a curve or add a reef that nearly ended them. These voyages stitched together continents, long before flight made distance feel small. Charts turned blank space into routes, and routes turned into trade, migration, and conflict. Port cities became crossroads where languages mixed and ideas traveled as quickly as cargo. Even mistakes mattered. A misplaced island could lure ships into danger, while a newly confirmed strait could redraw politics. The world we picture on a classroom map was earned the slow way, one perilous shoreline at a time. Magellan's voyage proved Earth could be circled by sea alone. When Magellan's expedition set out, it carried a daring idea. A ship could reach the same point it left without touching land routes at all. The journey became a grind of storms, shortages, and tension that turned crewmates into rivals. Magellan did not live to see the outcome, yet one battered vessel eventually completed the loop. The return was not a triumphant parade. It was proof carved out of endurance. A circumnavigation forced sailors to confront how huge the planet felt from deck level, where every day is measured by wind and water. It also revealed a practical truth. Oceans connect into one continuous system with passages that can be found and exploited if you can survive long enough to search. The voyage changed how people imagine distance. It made the world feel both larger in hardship and smaller in possibility, and it shifted global trade toward the sea. Captain Cook's charts were so accurate, sailors used them for generations. Precision at sea is more than pride. It is life or death. Captain James Cook earned a reputation for mapping coastlines with care that outlasted his era. He took repeated bearings, checked positions whenever skies allowed, and treated errors as debts that had to be repaid before moving on. The result was charts that helped later crews avoid reefs, find safe anchorages, and enter unfamiliar harbors with fewer surprises. His work mattered because the Pacific is unforgiving. Islands can be small, and a single misjudged mile can turn into a long drift with dwindling supplies. Accurate mapping also reshaped power. When a coastline is measured and named, it becomes easier to claim, govern, and exploit. Cook's charts, therefore, sit at a tense crossroads. They represent extraordinary skill and patient observation, and they also became tools that opened doors for colonization. The same line on paper could guide a ship and change a society. The Beagle voyage reshaped biology after Darwin watched life at sea. The Beagle set out to survey coasts, but it also carried a young naturalist with a restless notebook. During years at sea and on shore, Charles Darwin compared creatures and landscapes across wide distances. He saw patterns that felt too consistent to be chance. Similar animals appeared on different islands with small differences, as if shaped by local conditions. Fossils hinted that past worlds had held different forms of life, and living species seemed connected in ways people had not fully accepted. The voyage did not hand him a finished theory. It gave him questions that would not let go. Time at sea also gave him something rare: long stretches to think, revisit observations, and weigh evidence against belief. When his later ideas reached the public, they challenged how people understood nature and humanity's place in it. One expedition for mapping coastlines ended up mapping a new way of thinking, and the ripples spread far beyond any harbor. The HMS Challenger expedition founded modern ocean science in one journey. In the 19th century, the HMS Challenger set out on a mission that sounds almost impossible: measure the ocean, sample it, and describe it systematically across the globe. The crew lowered lines for depth, hauled up sediments, and collected water from different layers. They gathered specimens from places no one had physically visited, then shipped them back to be studied in detail. The work was slow and relentless. Every station required patience, coordination, and the willingness to repeat tasks in rough weather. What made the voyage revolutionary was its intent. It treated the sea as something that could be investigated with consistent methods rather than anecdotes. The Challenger's results filled volumes and shaped the language of oceanography. Depth, temperature, chemistry, and life were linked into one story. It also changed expectations. After that voyage, the ocean was not just a route to somewhere else. It became a subject worth exploring for its own sake. With mysteries that demanded careful measurement, Greek explorers measured seas, then argued where the world ended. Curiosity pushed Greek thinkers to treat geography as a problem that could be tested. Sailors brought back distances, coast shapes, and reports of currents. Then scholars tried to turn those scraps into a coherent picture. Some attempted early measurements of Earth itself, using shadows and angles to reason about scale. Others debated what lay beyond the known waters and whether the ocean was a boundary or a highway. These arguments mattered because they shaped decisions. A captain choosing a route needed practical guidance, and a city planning trade needed believable maps. The tension between observation and speculation became part of the culture of exploration. Not every claim was right, yet the method was powerful. Ask a question, gather what evidence you can, and accept that the sea might prove you wrong. That mindset, more than any single voyage, helped keep horizons moving outward. Polynesian navigators crossed open ocean using stars, swells, and seabirds. Across the Pacific, long before modern instruments, expert wayfinders treated the ocean like a readable landscape. They memorized star paths that rose and set in reliable patterns, and they paired those patterns with the feel of swells under a canoe. Different wave trains intersect, and trained bodies can sense that crossing like a hidden compass. Birds became clues, too. Some species fly out to feed at dawn and return toward land by evening, which can reveal an island still beyond sight. Clouds helped as well. Over shallow lagoons, light can brighten the underside of cloud decks in a way open water cannot. Navigation was not guesswork. It was an accumulated science carried in stories, chance, and apprenticeship. When crews reached a speck of land in a huge ocean, they proved something profound. Human knowledge can be portable, precise, and brave enough to cross emptiness. Viking longships reached North America centuries before Columbus sailed. Norse sailors built ships that were light, fast, and flexible enough to survive harsh seas. Their long ships could ride ocean swell and also slip into rivers, which meant exploration did not stop at the shoreline. From Scandinavia they pushed to Iceland, then to Greenland, and then farther west again at a site now called Lance Os Meadows. Evidence shows a Norse presence in North America, long before later European voyages. That reach was not magic. It was seamanship, timing, and a willingness to travel with only uncertain reports as a guide. These journeys show how exploration can happen in steps, with each new settlement becoming a launching point for the next. They also remind us that first depends on which story you were taught. The Atlantic was crossed and crossed again, long before it became a famous headline. The first deep soundings revealed oceans are far deeper than imagined. For a long time, many people pictured the seafloor as a nearby bottom, something a strong rope could reach without much trouble. Early deep soundings shattered that comfort. Crews lowered weighted lines until the cord vanished into darkness, and the waiting grew long enough to feel unreal. When the line finally came back, it carried a number that made sailors and scholars stare at each other. The ocean was not a shallow basin. It was a vast vertical world. That discovery changed everything. It affected where ships could safely anchor, how cables might be laid, and whether anyone could ever reach the deepest places. It also shifted imagination. If the sea had such depth, then it might hide landscapes like mountains and valleys, and it might hold life adapted to pressure no human body could endure. A simple act, dropping a line straight down, opened a new dimension of Earth. Exploration was no longer only horizontal. It became a descent into an unseen planet within the planet. Zheng He's treasure fleets dwarfed many European ships of the time. In the early Ming era, China launched vast state-sponsored voyages under Admiral Zheng He. The fleets carried soldiers, interpreters, craftspeople, and diplomats along with cargo meant to impress. They traveled through Southeast Asia and across the Indian Ocean, visiting ports where merchants already traded spice, textiles, and precious goods. These expeditions were about power as much as discovery. A large fleet arriving in harbor could settle disputes, secure alliances, and broadcast the authority of an emperor without firing a shot. Gifts moved outward and tribute flowed back, creating a political theater on the water. The sheer scale startled outsiders, and later stories about the ships became part history and part legend. Even without perfect measurements, the message is clear. Ocean exploration was never only a European project. Great maritime states rose elsewhere, and they used the sea as a stage for diplomacy and strategy. Phoenician sailors spread alphabets and trade across Mediterranean routes. Their world was stitched together by harbors, islands, and sharp headlands that demanded constant attention. They carried goods that people wanted badly, including metals, glass, and the famous purple dye that took enormous labor to produce. Yet their most lasting cargo was smaller than any amphora, a practical writing system that made record-keeping faster, deals clearer, and messages easier to copy. As ships moved from port to port, sailors and merchants shared not only products, but habits, words, and ways of counting value. Over time, letters traveled farther than the sailors who first used them. A symbol scratched on a shard in one coastal town could reappear in another, shaped by new tongues and new needs. Ocean routes became learning routes. Commerce and communication grew together, and the sea helped carry an idea that could fit in a human hand. Chinese sailors refined the compass, then trusted it on black seas. A compass seems simple until you imagine relying on it when clouds hide the stars and land is nowhere. The shift from coastal reference points to true open water navigation required a new kind of trust in an object that pointed steadily while the world moved unpredictably. Chinese mariners helped develop and apply magnetic direction finding, then used it to hold course when visibility failed. That reliability changed what a voyage could be. Ships could aim for distant targets with fewer stops, and merchants could plan routes that were not chained to sight of shore. The compass also changed decision-making on board. It gave captains a steady reference when arguments rose, fear set in, or storms scattered bearings. Ocean expeditions often hinge on tiny inventions that make vast spaces manageable. A small pointer floating or pivoting can become the difference between drifting in circles and arriving weeks later exactly where you intended. Longitude stayed a deadly mystery until accurate sea clocks arrived. Knowing latitude could keep you from drifting toward a hostile coast, but knowing longitude could keep you from vanishing entirely. For centuries, sailors could estimate east and west position only loosely, and small errors grew into enormous danger over long crossings. A ship might believe it was safely offshore, while reefs waited just ahead in darkness. This uncertainty turned navigation into anxious guesswork, and it made charts feel like promises that might break at any moment. Governments offered rewards, scientists argued, and captains kept sailing anyway because commerce and war did not pause for unsolved problems. The heartbreak is that the ocean punished honest mistakes. Crews did everything right, then struck land that should have been days away. Solving longitude did not make the sea safe, it made it legible. It turned the world's widest space into something you could measure with confidence. Medieval portolan charts captured coastlines with startling practical precision. These maps were built for use, not decoration. Portolan charts focused on coasts, harbors, and the angles between them, because that is what mattered when your ship was tired and the shoreline was dangerous. Their dense webs of lines helped navigators keep headings from port to port, and their careful outlines reflected knowledge accumulated through countless trips. What makes them so striking is how modern they can look in places sailors knew well. You can feel the hand of experience in every corrected bay and every carefully placed cape. The charts also reveal priorities. Inland regions are often vague, while the edge of the sea is sharp and confident for expedition history. They mark a turning point. Ocean travel was becoming systematic, shared, and repeatable. A captain did not have to rely only on memory or rumor. The map could carry collective knowledge forward, and that helped widen the radius of where people dared to sail. Early expeditions carried naturalists, artists, and translators alongside sailors. As voyages reached farther, leaders realized that discovery was not only about arriving, it was about returning with knowledge that could be shared. That is why many expeditions made room for people who did not steer or reef sails. Naturalists collected specimens, sketched anatomy, and noted behavior that could not survive a long trip in a barrel. Artists recorded coastlines, clothing, tools, and ceremonies with an immediacy that words struggled to match. Translators and interpreters made trade possible, reduced misunderstandings, and sometimes saved lives by catching a threat in time. These mixed crews turned a ship into a moving research station and a diplomatic mission at once. It also created tension because cramped quarters do not forgive differences easily. Still, the payoff was enormous. When a voyage returned, it could change libraries, museums, and policies, not just maps. Ocean expeditions became engines of culture as well as travel. Piracy followed shipping lanes like a shadow and forced new navies. Where wealth travels predictably, predators appear. As trade routes hardened into habits, pirates learned to wait where ships had to pass near straits, islands, and busy approaches to ports. Their success depended on speed, intimidation, and careful knowledge of tides and local geography. Merchant crews often had little chance. A pirate attack could strip cargo, seize a ship, or hold lives for ransom, all in minutes. The response changed maritime history. Nations began to fund stronger patrols, build better armed escorts, and coordinate convoys. Insurance markets grew, and ports tightened rules about papers and cargo. Even ship design shifted toward faster vessels that could escape trouble. Piracy also created its own mythology, but the reality was more practical and more frightening. It was organized crime on the high seas, and it fed on the same global connections that made cities rich. The ocean became a chessboard where commerce and violence learned each other's moves. The Trieste became the first vessel to reach the deepest point on Earth and return safely. In the early 1960s, the bathyscaphe Trieste carried 2 men into the deepest known part of the ocean. The descent took hours, and light fell away until the world outside the window was black. Pressure climbed to a level that would crush ordinary structures, so the crew depended on a strong pressure sphere and careful engineering. Along the way, the vehicle passed through layers with different temperatures and densities, each one a boundary between worlds. At the bottom, the seafloor was not a dramatic cliff. It was a quiet expanse of sediment stirred by the slightest movement. The achievement was not just reaching the depth, it was returning. Coming back proved that humans could visit the Hadal Zone and survive the trip. That single dive became a symbol of what exploration can do when curiosity meets craftsmanship. it also set a challenge that still feels mythic. If people can touch the deepest point, then the ocean's remaining unknowns are not beyond reach, only beyond routine. Ancient Egyptians sailed the Red Sea for incense and rare woods. These voyages were not casual coastal hobs. Crews moved through heat, reefs, and sudden winds that could grind a ship into splinters. The goal was treasure you could smell and touch. Resins burned in temples, timbers that could not be found along the Nile, and materials that made royal ceremonies feel connected to far horizons. Getting to the water could be as hard as the sailing. Supplies had to be gathered, holes had to be prepared, and departures had to match seasons that make return possible. When an expedition came home, it proved that planning could stretch beyond desert borders and into open water. It also proved that exploration often begins with desire, not glory. A craving for sacred scent and strong wood was enough to pull ships into the unknown. Roman grain fleets fed cities, and storms could topple empires. A great city can be conquered without an army if its food stops arriving. Roman power depended on massive shipments of grain crossing open water, especially when local harvests could not meet demand. Ships became floating lifelines. When seas were calm, the system looked unstoppable. When weather turned, it became frighteningly fragile. A delayed convoy could mean hunger, unrest, and political crisis that spread faster than any rumor. This is one reason Rome invested in ports, warehouses, and naval protection, and why captains studied seasonal patterns with almost religious seriousness. The sea was both road and threat. It could deliver abundance, and it could erase it overnight. Ocean expeditions in this era were not always about discovery. They were about keeping daily life alive at imperial scale. Every successful crossing was a quiet victory. Every wreck was a reminder. But nature still held the upper hand. Arab and Swahili sailors rode monsoon winds across the Indian Ocean. In the Indian Ocean, wind itself sets the schedule. Monsoon patterns shift direction with the seasons, which means a voyage is planned like a promise made to the sky. Sailors along the Arabian coasts and the Swahili city-states learned to depart when the winds would carry them outward, then return when the winds changed and pulled them home. This seasonal rhythm created a stable web of trade and travel linking East Africa, Arabia, India, and beyond. Ports became multilingual, meeting places where ivory, gold, spices, and textiles moved alongside stories and faiths. Navigators built knowledge that was practical, repeatable, and shared across generations. The ocean was not a blank space to fear. It was a timed corridor that rewarded patience and punished impatience. When you understand the winds, the distance between continents shrinks. What looks like a barrier becomes a bridge that opens, closes, and opens again. Norse sunstones may have helped find direction on cloudy days. Imagine standing on deck with a gray sky above and no clear sun to guide you. Some researchers have suggested that certain crystals could help reveal the sun's position through polarized light, even when clouds hide it. The idea is not settled as simple proof, and the surviving sources are tangled with legend. Still, the possibility is fascinating because it shows how navigation can borrow from the natural world in surprising ways. If a sailor could glint direction from a stone and careful observation, then overcast seas would feel less like a locked door. It also fits a broader truth about long voyages. Mariners will test anything that might reduce uncertainty. From bird behavior to wave field to the color of the horizon. Whether sunstones were common tools or rare tricks, the story points to ingenuity under pressure. When you cannot see the sky clearly, you learn to read light itself. The astrolabe lets sailors read latitude from the height of stars. On a moving deck, precision is hard won. Yet the astrolabe gave mariners a way to measure the angle of a familiar star or the sun above the horizon, then translate that angle into latitude. It did not solve every problem, and rough seas could turn a careful reading into a guess. Still, it changed the mental map of a voyage. A ship could know how far north or south it had wandered, which made return routes safer and long crossings more confident. It also gave exploration a new kind of discipline. Observation became a routine task, repeated night after night with results recorded and compared. That rhythm turned the sky into a partner in navigation. When you can measure where you are on a north-south line, the ocean stops being pure uncertainty. It becomes a grid you can enter deliberately. For sailors, that shift was thrilling. It meant the heavens could guide you across water that offered no landmarks at all. The cross staff measured the heavens and burned many eyes. This tool was simple in design and brutal in practice. A sailor held the staff to the face and slid a crosspiece until it lined up with the horizon and the sun or a star, then read the angle from markings. Used at night with stars, it could be manageable. Used with the sun, it was hazardous. Staring toward bright light for repeated readings could damage eyesight, and sailors paid for accuracy with pain and risk. Yet crews kept using it because knowledge at sea has a price and ignorance costs more. The cross staff represents the gritty reality behind elegant navigation stories. Instruments were not magic. They demanded steady hands, clear skies, and bodies willing to suffer for a better position line. This is the texture of expedition history. The grand arc of discovery is built from small, uncomfortable moments where someone squints into glare because a single degree could mean missing land by miles. John Harrison's chronometers turned timekeeping into a life-saving tool. The solution to longitude arrived through time itself. If you could keep the time of a home port while sailing far away, you could compare it with local noon and calculate how far east or west you had traveled. That sounds simple until you remember what ships endure. Rolling decks, salt air, temperature swings, and constant vibration can destroy delicate mechanisms. John Harrison spent years building clocks that refused to drift even when the ocean did its best to shake them apart. His chronometers were not just clever machines. They were portable certainty. A captain with reliable time could plot a position that matched reality, not hope. That changed outcomes in a way maps alone never could. Voyages became more direct. Landfalls became less accidental, and reefs became avoidable more often than not. In expedition history, few objects are as dramatic as a clock that keeps its promise in a storm. Dead reckoning worked until currents quietly stole ships off course. Dead reckoning feels reassuring because it uses what you can see and feel: speed through the water, direction on the compass, and time since the last known position. Add it up and you get a tidy estimate of where you should be. The ocean, however, has its own math. Currents slide beneath a hull like invisible rivers, pushing ships sideways without changing the wind in the sails. A crew might steer faithfully for days only to discover that the sea has been carrying them diagonally toward danger. That is why a landfall could arrive with shock or not arrive at all. Dead reckoning also depended on judgment. A tired sailor's speed estimate, a worn line, or a small steering error could compound into miles. Explorers learn humility from this. The sea can be navigated, but it cannot be buoyed. When the water moves, it moves the map with it. Ship logs became scientific records, one careful entry at a time. A ship's log began as a tool for discipline and accountability, yet it quietly became a treasure for science. Each day demanded notes on wind direction, cloud cover, sea state, and the ship's progress. Over months, those entries turned into patterns. A single captain might notice seasonal shifts, but thousands of logs across decades revealed something bigger: where storms were common, where calms lingered, and how currents behaved in different regions. The log also captured the human side of exploration in plain language: broken masts, strange lights, unfamiliar birds, and the emotional weather of the crew. Later, researchers learned to read these pages as data, even when the writers never imagined that future. It is one of history's quiet miracles. Ordinary routine produced a long record of the ocean's moods. The sea changed from a collection of stories into a place that could be compared, mapped, and studied. Sailors learned ocean swells can point to land beyond sight. Land announces itself in ways that are easy to miss if you are not trained to notice. Long before a shoreline appears, islands can shape the water around them. Swells reflect, refract, and interfere, creating patterns that experienced sailors can feel through a hull. The rhythm of the sea changes, and that change can act like a distant signpost. Near land, you might also meet floating debris, different seabirds, or a subtle shift in the color of water. Yet the swell is the most constant companion. It travels great distances and carries information like a messenger. This kind of knowledge is hard to write down and easy to dismiss, which is why it was often misunderstood by outsiders. On the ocean, it is practical and powerful. When you can sense direction from moving water, the horizon stops being a wall. It becomes a veil that can be read and sometimes crossed with confidence. The trade winds became highways that shaped exploration and colonization. In the tropics, the atmosphere sets up reliable belts of wind that blow with remarkable consistency. Sailors learned that these trade winds could carry ships westward with speed that felt almost effortless if you entered the right latitude. Returning often meant finding a different band of wind, which created looping routes that shaped where ships traveled and where ports grew wealthy. Once those wind patterns were understood, exploration changed tone. Voyages became planned systems rather than one-off gambles. That efficiency fed expansion, and expansion fed conquest. Colonization did not happen only because people wanted land. It happened because wind made regular crossings possible, and regular crossings made control plausible. The trade winds are therefore more than weather. They are part of the hidden machinery of history. They guided explorers toward new shores, and they also guided violence, forced labor, and extraction. A steady breeze can carry civilization's brightest ambitions and its darkest consequences. The doldrums trapped ships for weeks with heat and hunger. Near the equator, sailors feared a region of weak shifting winds, where sails hung limp and progress nearly stopped. A ship could sit under a blazing sun while the sea looked calm enough to mock you. Water stores warmed and tasted foul. Food spoiled, tempers flared, and discipline became harder to maintain with each stalled day. The psychological strain was intense because you could see endless ocean and still feel imprisoned. Then, without warning, violent squalls could erupt, dumping rain and tearing at rigging as if the sky had changed its mind in anger. Expeditions planned around this zone, yet many were forced into it by currents or bad luck. The doldrums reveal something important about ocean travel. Danger is not always dramatic. Sometimes it is stillness. Sometimes the threat is time itself, stretching until supplies and hope begin to thin. For explorers, learning to endure that pause was as important as learning to ride a storm. Scurvy killed more crews than cannons until citrus changed naval history. On long voyages, sailors began to fail in a strange and terrifying way. Gums swelled and bled. Old wounds reopened. Legs grew weak, and exhaustion turned ordinary work into agony. Ships could leave port with strong crews and arrive with ghosts. The tragedy is that scurvy was not a mystery of monsters or curses. It was a nutritional collapse driven by months without fresh sources of what we now call vitamin C. For centuries, expeditions treated it with superstition, resignation, or useless remedies. Meanwhile, the sea kept collecting bodies. When effective prevention finally spread, it changed more than health. It changed strategy. A nation that could keep crews alive could sail farther, stay longer, and return more reliably. The ocean did not become kinder. Humans became better prepared. A simple fruit carried and rationed with care helped transform voyages from slow attrition into sustained exploration. Captain Cook's diet experiments showed prevention could be organized and routine. Some commanders treated sickness as fate, but Cook treated it as a problem with levers you could pull. He insisted on shipboard habits that sounded ordinary yet proved revolutionary. Cleanliness, ventilation, and strict attention to food quality reduced the slow decay that haunted long voyages. He pushed for provisions that could last, and he tested foods that helped crews stay functional over months at sea. The key was not one miracle meal. It was the idea that health could be managed through consistent policy, even in cramped wooden worlds surrounded by salt water. That approach changed expectations. Crews began to believe that survival was not only courage and luck, It could be planning, routine, and leadership that cared about the unglamorous details. This matters for expedition history because it links exploration to logistics. Great journeys are often won in stores and kitchens, not only on open decks. When sailors stopped dying in predictable waves, the map of what was possible expanded. The Manila galleons stitched Asia and the Americas into one ocean route. Imagine a single sailing route that carried silver one way and silk, porcelain, and spices the other, year after year, across the widest ocean on Earth. The Manila galleons did exactly that, linking the Philippines and New Spain in a circuit that helped build an early form of globalization. The crossing was long and punishing. Ships had to time departures, ration water, and survive storms that could shred rigging like paper. Crews faced isolation that tested morale as much as skill, yet the reward was enormous. A successful voyage could reshape markets, fund governments, and fill cities with goods that felt almost magical to people who had never seen them. Ports became melting pots where languages, foods, and customs mixed under the pressure of profit and distance. This was not just trade. It was a dependable ocean bridge that proved the Pacific could be crossed on schedule, not only on daring luck. The Atlantic slave trade was an enforced crossing, not exploration. This was not a story of brave discovery. It was a system of violence that turned ocean routes into machinery for human suffering. People were captured and forced onto ships, then carried across the Atlantic under conditions designed for profit, not survival. The crossing stripped names, families, and futures, and it fed plantations and empires with stolen labor. Some ships became floating prisons where illness spread quickly and despair was constant. Resistance happened in many forms, from refusal to eat to sabotage to uprisings at sea, even when the odds were crushing. The legacy did not end at the shoreline. It shaped economies, laws, and identities across multiple continents, and it left scars that still matter. When we talk about ocean history, this crossing has to be faced honestly. It shows that the same ocean that carried ideas and goods also carried cruelty at industrial scale, and that remembering is part of justice. Privateers blurred war and commerce across contested seas. A privateer looked like a merchant captain, until the moment profit and patriotism aligned. Governments issued legal commissions that allowed privately owned ships to attack enemy commerce, capture cargo, and sell prizes, while sharing proceeds with crews and backers. This turned conflict into a business model. A bold voyage could make a fortune, and it could also weaken an opponent without a formal battle. The line between lawful capture and outright piracy was thin in practice, and arguments over paperwork could decide whether someone was celebrated or hanged. For expeditions, the effect was chilling. Trade routes became battle zones, and even neutral ships could be harassed or mistaken for enemies. Ports buzzed with rumors about raiders, and captains sailed with both charts and caution. Privateering shaped strategy because it attacked the lifeblood of empires, which was shipping. It also created careers for daring seamen who learned to navigate not only oceans but laws, alliances, and shifting definitions of legitimacy. Mutinies erupted when leadership failed, and voyages became rebellions. A ship is a small world with no easy exit. When food runs low, pay feels uncertain, or discipline turns cruel, resentment has nowhere to drain. It builds with every watch and every order. Mutiny can begin quietly with whispered agreements and shared anger, then explode in a moment when the crew decides fear is no longer a reason to obey. Some mutinies were desperate attempts to survive bad command. Others were power grabs fueled by grievance and ambition. Either way, they reveal the fragile social contract that keeps an expedition moving. A captain holds authority, but the sea holds everyone. If the crew stops believing the voyage is worth the risk, the mission can collapse overnight. The aftermath could be grim. Mutineers might face trials, exile, or execution, even if their complaints were real. Yet, mutinies also forced navies and companies to confront conditions on board. They show that exploration history is not only about maps. It is also about human limits under pressure. Shipwrecks built underwater museums that still trap cargo in sand. A wreck is a time capsule sealed by cold, salt, and darkness. When a ship goes down, it carries its moment with it. Tools, ceramics, coins, cannons, personal letters, and ordinary objects that rarely survive on land. Over time, currents bury and reveal these fragments like a slow turning page. Archaeologists can read trade patterns from a scattered cargo or reconstruct a storm from the way timbers broke apart. Sometimes the sea preserves astonishing detail. Wooden hulls can last when oxygen is scarce, and sealed containers can protect delicate goods for centuries. Yet wrecks are not treasure chests in a story. They are often graves, and they demand respect. They also challenge ownership. Who has the right to what the sea kept? Expeditions to wreck sites have become voyages of both science and ethics. Each dive asks the same question: are we learning or are we taking? The best work treats the seabed as a museum without walls and as a memorial that deserves care. Salvage divers recovered treasure, then accidentally advanced diving technology. Salvage began as a race against time and water. Cargo was valuable, and storms or shifting sand could hide it forever. Divers went down with simple gear, poor visibility, and enormous risk, often working by touch alone. Pressure-crushed lungs, nitrogen-confused minds, and equipment failures could turn a plan into tragedy in seconds. To survive, crews improvised. They refined air pumps, improved hoses, developed better helmets and valves, and learned hard lessons about ascent and decompression. Innovation followed danger like a shadow. What started as a hunt for coins and cannon often produced techniques that later supported science, construction, and rescue. Salvage also changed how people imagined the underwater world. The seafloor stopped being a place only fish could visit. It became a workplace and later a research frontier. In a strange way, greed and curiosity sometimes traveled together. The desire to recover lost wealth pushed humans to build tools that opened the deep for many other purposes, including archaeology and engineering. The first submarine cables turned oceans into global message corridors. Before undersea cables, news crossed oceans at the speed of a ship. A war could end before a distant capital even heard it had begun. Submarine telegraph cables changed that relationship with time. Messages could travel in minutes, which transformed diplomacy, finance, and journalism. Suddenly, markets could react quickly. Governments could coordinate across continents, and families could receive short updates that once would have taken months. The engineering challenge was immense. Cables had to survive salt water, pressure, abrasion, and the constant motion of currents. Insulation had to resist decay, and the cable had to be laid without snapping under its own weight. Failures were common, and each failure taught painful lessons about materials and seafloor terrain. When the working line finally held, it felt like magic made practical. The ocean did not shrink physically, but it shrank emotionally. Distance became less lonely and more connected, and the sea became not only a route for ships, but a pathway for information. Cable-laying ships mapped seafloors long before sonar existed. To lay a cable safely, you need to know what lies beneath you. Steep drops, sharp ridges, and rough bottoms can grind a line until it fails. Long before modern sonar images, cable crews built knowledge with soundings, tension readings, and careful observation of how a cable behaved as it unspooled. Every time the line snagged, scraped, or suddenly went slack, it hinted at the shape of the unseen seafloor. Over many projects, those hints became a rough portrait of underwater geography. Valleys, plateaus, and unexpected mountains began to emerge in the mind of engineers and navigators. This work was not glamorous, but it was revolutionary. It turned the abyss from a blank on the map into a landscape with features and hazards. The goal was communication, but the side effect was discovery. In a practical industry, the ocean quietly revealed its contours. Cable ships became accidental explorers, writing early chapters of seafloor mapping with every careful mile they laid. Storm forecasting began with mariners who compared patterns across oceans. Long before satellites, sailors treated the sky like a living document. They watched cloud shapes, pressure changes, wind shifts, and the color of the horizon. A single captain might recognize danger, but broader forecasting required shared memory. Over time, mariners began comparing observations from different voyages and different regions. Patterns appeared. Certain wind directions preceded certain seas. A sudden calm could be a warning, not a gift. Pressure dropping steadily could mean trouble, even if the day looked fair. Ports, navies, and later meteorologists started collecting reports, then building early charts of storms and seasonal behavior. This changed expedition planning. Captains could choose safer windows, avoid known cycles, and take warnings more seriously than superstition. Forecasting did not remove risk, but it gave ships a fighting chance. It also highlights a beautiful truth about exploration. The ocean teaches by repetition. When people listen carefully and share what they learn, the sea becomes a little more predictable and far more understandable. The search for a northwest passage drove centuries of Arctic suffering. For generations, European powers chased a shortcut that promised enormous profit. A sea route across the top of North America would bypass long voyages and hostile rivals. So ships pushed into ice-choked waters with hopes that often outweighed preparation. The Arctic answered with darkness, crushing pressure, and a cold that turned simple tasks into exhausting work. Crews fought scurvy, frostbite, and hunger, while the ice decided whether they moved at all. Ships could be trapped for a whole season, and the waiting could break morale as surely as a storm breaks a mast. Expeditions kept going because the reward felt like a key to the world's trade. Many returned with little more than hard lessons, and many did not return at all. The Northwest Passage search is a reminder that exploration is not always heroic. Sometimes it is a long series of losses. Paid in human endurance, Franklin's lost expedition became a cautionary tale of overconfidence. When Sir John Franklin sailed into the Arctic, the venture carried confidence, prestige, and the belief that modern organization could solve ancient obstacles. 2 ships, trained crews, and supplies meant to last were supposed to turn a daunting route into a manageable plan. Then the ice closed in, and the plan stopped mattering. The expedition vanished into a landscape that does not forgive delays, and the years that followed became a grim mystery for families and governments. Search parties later found traces that suggested hunger, cold, and desperate decisions as conditions worsened. What makes the story so haunting is how ordinary the beginning looked. Orders were issued, decks were scrubbed, and optimism held steady right up until the environment changed the rules. The loss became a warning that technology and rank do not guarantee safety. In the Arctic, humility is not a virtue, it is a survival tool. The Franklin expedition taught later explorers to respect limits and to plan for the moment when confidence fails. Inuit knowledge guided survival where European maps turned useless. In the far north, local expertise was not an extra. It was the difference between living and disappearing. Inuit communities understood sea ice as a shifting terrain with safe paths, dangerous pressure ridges, and seasonal rhythms that outsiders often misread. They knew how to travel when visibility vanished, how to find food where a stranger saw only white, and how to interpret subtle weather signs that arrived before a storm broke. Their tools and clothing were adapted to the environment, built from materials that worked because they were tested for generations. When European expeditions struggled, Inuit guidance could mean better routes, better shelter, and better decisions. This knowledge was frequently dismissed or undervalued, even as it saved lives. That is one of the sharpest lessons of ocean exploration history. The most advanced map can fail if it is not grounded in lived experience. Listening matters, respect matters, partnership matters. In a place where mistakes compound quickly, shared knowledge becomes the most precious cargo aboard any journey. Antarctic expeditions proved endurance could outrun even modern planning. The Antarctic was explored in an age of stronger ships and growing scientific confidence. Yet it still demanded a kind of stubborn resilience that no blueprint could fully provide. Crews entered a continent of wind, glare, and isolation. where the cold is not a temperature, but a constant pressure on every decision. Equipment failed, fuel ran low, and weather could erase progress for days. Even well-supplied parties faced the problem of distance because every mile had to be hauled across ice, often against the wind. What kept many expeditions alive was not flawless strategy. It was the ability to adapt when plans cracked. Teams learned to repair what they had, ration what they feared losing, and keep moving even when the landscape offered no obvious reward. Antarctic history is full of moments where survival hinged on attitude, teamwork, and relentless small choices. It shows that exploration is not only about reaching a goal, it is also about learning how to persist when the world refuses to cooperate. Shackleton's crew survived, and the rescue became legend without a death. Ernest Shackleton's endurance became trapped and then destroyed by ice, turning an ambitious expedition into a fight to keep every person alive. What followed was leadership at its most practical. He kept his crew focused on routines, morale, and the next achievable step. Even when the horizon offered no comfort, they camped on drifting ice, then took to small boats across dangerous seas, aiming for a chance of land and help. The odds were brutal. Freezing spray, exhaustion, and constant risk of capsizing could have ended the story at any stage. Instead, Shackleton pushed on with a small party to seek rescue, then returned for the others. The result is famous because it refuses the usual arc of triumph or tragedy. The central victory was not a new coast or a scientific prize. It was bringing everyone home. The rescue became a lesson in crisis leadership and in how determination can be shared rather than imposed. In ocean expedition history, few stories show the power of human resolve more clearly. Nansen's Fram drifted with ice to test a radical theory. Fridtjof Nansen proposed an idea that sounded like surrender to many listeners. Instead of fighting the Arctic ice, he would let it carry his ship. The Fram was built to survive pressure by being shaped to rise as ice squeezed. Then the crew intentionally froze into the pack. Months turned into years as the ship drifted with currents that were poorly understood, proving that the ice itself could be a moving platform. This was not passive waiting. It was disciplined observation, careful rationing, and constant readiness for sudden change. The experiment tested a bold theory about Arctic drift, and it also tested human patience. Imagine knowing you are traveling, yet seeing almost no scenery change day after day under a ceiling of cold. The Fram voyage shows a different style of exploration. Sometimes the best way forward is not to force motion, but to cooperate with the environment's own movement. It is exploration by trust, engineering, and nerve, and it changed how later expeditions thought about polar travel. The first crossing of the Southern Ocean humbled nearly every ship. The Southern Ocean has a reputation that was earned the hard way. Winds can roar without warning. Waves can build into moving walls, and cold water punishes mistakes with frightening speed. Early ships that tried to cross these latitudes met seas that felt alive, rising and breaking with a force that made rigging scream and timbers groan. Navigation was harder because storms could block celestial sightings for long stretches, and icebergs added danger when visibility was poor. Crews were soaked, tired, and constantly repairing, often while trying to sleep in a world that never stopped moving. The lesson of early crossings was simple. Skill matters, but conditions can still overwhelm skill. The Southern Ocean forced sailors to respect latitude as a factor in risk, not just a line on a chart. It also pushed shipbuilders and captains to improve design, seamanship, and planning because survival demanded it. When a vessel finally cleared those waters, the relief was not pride, it was gratitude. Whaling voyages created global charts, a terrible ecological cost. Whalers pursued animals that traveled widely, so their work took ships into remote seas long before many scientific expeditions arrived. Captains recorded routes, currents, and landmarks because success depended on finding whales again and again. Over time, that practical record built a kind of rough world map, one shaped by pursuit and profit. Yet the knowledge came with a devastating price. Whale populations were hit hard, and some species were pushed toward collapse as demand grew for oil, baleen, and other products. These voyages also transformed coastal economies, building fortunes and fueling industries. While the living resource that supported them diminished, the history is uncomfortable, and it should be. Ocean expeditions often mix curiosity with extraction, and whaling is a vivid example. It expanded human reach into distant waters, and it proved that the ocean's abundance is not unlimited. When modern conservation emerged, it was partly because people finally saw the cost of treating wildlife as an endless supply. The charts remained, but the missing whales became a quieter, harsher map of consequence. Naval battles pushed ship design, then science borrowed the improvements. War at sea is a brutal laboratory. When survival depends on speed, stability, and endurance, navies invest in better hull shapes, stronger materials, and more reliable steering and signaling. Battles exposed weaknesses quickly. A ship that handled poorly in heavy seas could lose before a cannon fired, and a design that saved seconds in maneuvering could decide a campaign. Those innovations did not stay confined to conflict. Explorers and scientists later benefited from sturdier vessels, improved navigation rooms, and better equipment storage because the same traits that help in battle also helped in storms and long voyages. Stronger ships could carry heavier instruments, survive harsher weather, and stay at sea longer without falling apart. In this way, military pressure indirectly widened the frontier of research. It is a complicated inheritance. The ocean's greatest tools were sometimes forged for violence, then repurposed for discovery. Ocean expedition history often sits in this uneasy overlap, where progress and peril traveled together. The transition from sail to steam rewrote what distance meant at sea. Sailing ships depended on wind and weather, which meant travel time could feel like a negotiation with the sky. Steam changed that relationship. With engines, a ship could move when the air refused to cooperate, and routes became more predictable. That predictability altered everything from passenger travel to naval strategy to scientific. It also changed ports. Steamships needed fuel, repairs, and specialized infrastructure, so networks of coaling stations and service hubs gained new importance. At the same time, the romance of sail gave way to the grind of machinery, heat, and constant maintenance. A voyage became less about waiting for the right breeze and more about managing an industrial system at sea. For expeditions, steam offered new reach, but it also brought new vulnerability, because fuel shortages or mechanical failures could strand a ship just as surely as calms once did. The real shift was psychological. Oceans still spanned the globe, but the feeling of helplessness began to fade. Distance became something you could plan for, not simply endure. Coaling stations became stepping stones that decided which empires could roam. Steam power promised freedom from wind, yet it changed ships to fuel. A navy or trading company could only project strength as far as its next reliable coal supply, so distant ports became strategic prizes. A small harbor with good storage could suddenly matter more than a rich inland city because it kept engines moving and schedules intact. Rival powers competed for these points on the map, negotiating leases, building depots, and sometimes seizing territory to secure a refueling stop. A ship that arrived to find an empty bunker was not just delayed, it was vulnerable, stranded between oceans and politics. Coaling itself was exhausting work with dust, heat, and tight timing that could turn a port call into a frenzy. These stations shaped shipping routes like beads on a string, and that string often decided whose flag could appear regularly in faraway waters. The opening of the Suez Canal rerouted expeditions and reshaped geopolitics. When the Suez Canal opened, it cut a doorway between the Mediterranean and the Red Sea, and the world's sea travel suddenly bent around it. Voyages that once swung far around southern Africa could be planned with a new, shorter spine through Egypt. That shift did more than save time. It changed which ports thrived, which fleets could respond quickly, and which regions became urgent to control. Expedition planning became less seasonal in some routes because ships no longer had to gamble on the long haul around the Cape. The canal also concentrated vulnerability. A narrow passage can become a pressure point where blockades, accidents, and political disputes ripple outward into global trade. For explorers, it meant faster access to the Indian Ocean and beyond. For empires, it meant strategy now had a choke point, and choke points attract attention, conflict, and ambition. The Panama Canal shortened voyages and changed ocean strategy overnight before the Panama Canal. Moving a ship between the Atlantic and Pacific could mean a punishing trip around South America, where winds and seas tested every plank and every crew. The canal turned that ordeal into a controlled passage through locks and lakes, and naval strategy shifted almost immediately. Fleets could be redeployed faster, and shipping companies could design routes with new efficiency. Ports on both coasts gained new importance while older waypoints lost traffic. Expeditions also changed shape. A scientific vessel could plan multi-ocean work without committing months to rounding Cape Horn, and supply lines could be scheduled with fewer unknowns. Yet the canal came with its own drama. Engineering had to tame tropical disease, heavy rains, and unstable ground, and operations depended on careful coordination. A single corridor now connected two immense basins. The ocean world became more integrated, and the map of power tightened around a man-made hinge. The Great Circle route made maps lie, yet ships arrive sooner. On a flat map, the straight line between two ports looks obvious, but Earth is curved, and the fastest path is often an arc. Great Circle navigation embraces that curve, sending ships along routes that can appear bent or even wrong on common projections. To a new sailor, it can feel like steering away from the destination on purpose. Yet, the math is honest. The globe's geometry can shorten distance, save fuel, and reduce days at sea. This idea changed how captains thought about planning because it forced them to trust calculations over intuition and over the deceptive comfort of straight lines. On paper, it also required careful navigation since heading must be adjusted as the route curves across latitude. Great Circle routes remind us that exploration is not only about finding new places, it is also about learning the true shape of the world you already live on and letting that truth guide you. Ocean currents were measured with bottles, then with drifting instruments. Before satellites and digital sensors, oceanographers used simple objects to ask a vast question. Where does the water go? They sealed messages in bottles or released marked floats, then waited for a stranger on a distant shore to report where the sea had carried them. Each return was a data point delivered by chance and patience. Over time, patterns emerged that hinted at highways of moving water, loops and boundary currents that could speed a voyage or sabotage it. Later, purpose-built drifters made the method more reliable. These instruments could transmit positions, ride at chosen depths, and reveal currents that were invisible from a ship's deck. The romance of a bottled note gave way to steady tracking. Yet the core idea stayed the same. Let the ocean move something for you. Then read the story, written in its path. Currents became measurable, and that changed navigation, climate study, and search operations at sea. The first global tide tables came from years of patient coastal watching. Tides look simple until you try to predict them in a new port, with a reef at the entrance and a narrow window for safety. Early tide tables were built from relentless observation, with people recording water heights, day after day, in all seasons to storms and calm. Those records revealed cycles that could be trusted, and they turned coastal navigation into something closer to scheduling than gambling. A captain could plan an arrival for high water, avoid grounding, and time a departure to catch a favorable current. Tides also mattered for exploration landings. A boat that reached shore at the wrong moment could be stranded, smashed, or unable to return to the ship. By gathering long records across many places, scientists and mariners began to see tides as a global system influenced by the moon, the sun, and local geography. The tables were quiet triumphs of patience, turning the ocean's daily rise and fall into a usable forecast. Deep-sea trawls pulled up creatures that looked like invented monsters. When early expeditions dragged nets through deep water, many expected emptiness. Sunlight does not reach those depths, and for a long time people assumed life could not thrive there. Then the trawls came up heavy, dripping with animals that seemed to break the rules of familiar nature. Some were translucent, some had enormous mouths, and some carried their own light like floating lanterns. The shock was not only visual. It challenged the idea that the deep ocean was barren. It suggested that life could adapt to cold, pressure, and darkness in ways humans had never imagined. Each haul became a suspenseful reveal because nobody knew what form might rise from the black. These finds also raised new questions. How do animals find food where it is scarce? How do they reproduce in the dark? Deep trawls made the ocean feel less like a void and more like a hidden biosphere, rich with surprises that had been living beneath ships all along. The bathysphere showed humans could descend even without a submarine. Picture a steel sphere hanging beneath a ship on a cable, lowering into darkness while the surface shrinks to a coin of light. The bathysphere was exactly that, a tiny chamber for two people with thick walls, small windows, and no ability to move on its own. It was not a submarine in any heroic sense. It was a controlled drop into pressure that could crush weaker metal. What made it revolutionary was direct human presence at depth. Observers could look out and describe what they saw in real time, not as a specimen hauled up, damaged and dead. They reported strange lights, drifting animals, and the feeling of being suspended in an alien column of water. The bathysphere proved that descent was possible with careful engineering and nerve. It also reframed exploration. You did not need to travel across the sea to find a new world. You could find it straight down beneath your own hull. Early diving suits made sea pressure survivable, but movement stayed clumsy. The first heavy diving suits turned a human into a walking experiment. A hard helmet, weighted boots, and air supplied from above allowed divers to work below the surface for longer than breath could ever permit. Pressure that would squeeze lungs became manageable, and tasks like inspection, repair, and salvage moved into new territory. Yet mobility was the price. Divers shuffled rather than swam, and every step could snag a line or sink into mud. Communication was limited, and a simple problem, like a twisted hose or a stuck valve, could become a life-threatening emergency. Visibility was often poor, so work was done by touch, by patience, and by trust in the crew above. These suits did not make the sea friendly. They made it reachable. They also changed how people imagined the boundary between land and ocean. The seabed became a place humans could visit on purpose, even if every movement felt slow, heavy, and unnatural. Sonar turned the ocean from mystery into echo and distance. In fog, darkness, or deep water, sight fails quickly. Sonar offered a different sense, one built on sound. A pulse goes out, a reflection returns, and time becomes a measuring stick for distance. That simple idea transformed ocean travel and exploration. Submerged hazards could be detected. Depths could be mapped, and objects could be located in places where a line and wait would take too long. Sonar also changed how people pictured the seafloor. Instead of an abstract unknown, it became a surface with slopes, peaks, and trenches that could be traced in sweeping passes. For expedition crews, this meant new confidence and new responsibility. If you can see with sound, you can plan with more precision, and you can take on projects that once felt impossible, from safer navigation to systematic surveying. Sonar did not remove the ocean's power. It gave humans a way to listen to it and to turn that listening into knowledge. World War depth charges forced new understanding of undersea warfare. In the First World War, the ocean stopped being only a surface battlefield. Submarines turned invisibility into a weapon, and navies scrambled to answer a threat they could not easily see. Depth charges were a blunt reply. Explosive barrels dropped into guessed positions set to detonate at chosen depths. Each attack became an experiment in sound, timing and pressure. Crews listened for propellers, watched for oil, and tried to imagine a target moving in 3 dimensions. When a charge exploded, it did not need a direct hit to be devastating. Shock waves could crack holes, disable systems, or force a submarine to surface in panic. This pressure drove rapid innovation, better listening gear, better tactics, and better coordination between ships. It also changed how people studied the sea. Suddenly, temperature layers and underwater acoustics mattered to survival. Wartime urgency pushed ocean knowledge forward, and it did so at a frightening cost. Convoys crossed the Atlantic, and statistics became a survival tool. When submarines hunted merchant ships, the Atlantic became a numbers game with human stakes. Sailing alone meant you could vanish without witnesses. So convoys grouped ships together under escort, turning scattered targets into a defended formation. The decision was not only emotional, it was mathematical. Planners measured loss rates, route choices, escort coverage, and the probability of encounter. Small improvements in timing or spacing could save hundreds of lives and millions of tons of cargo. Weather reports, radio intelligence, and patrol patterns all fed into constant recalculation. Even the zigzagging of ships was debated as a trade between safety and fuel. This was a new kind of ocean expedition, a moving city of steel and worry, crossing dark water while knowing an enemy might be listening. In that setting, statistics were not cold abstraction. They were hope expressed in planning. The convoy system showed that survival at sea can depend on discipline, cooperation, and the courage to trust careful analysis. A Titanic disaster sparked modern safety rules for ocean travel. When Titanic sank, it was not only a ship that went down, it was a belief that size and prestige could outrun the sea. The shock exposed painful gaps in safety culture. Lifeboat capacity, radio watch practices, and emergency drills were suddenly seen as matters of life and death, not optional extras. The aftermath pushed governments and shipping companies towards stricter standards, including round-the-clock distress monitoring and better requirements for life-saving equipment. Routes through ice waters were reconsidered and ice reporting became more formalized. What makes the tragedy so lasting is its mix of grandeur and vulnerability. A marvel of engineering met ordinary hazards, cold water, darkness, and human delay. Ocean travel became safer because the world paid attention and because rules were written in response to a single night of irreversible consequences. In expedition history, it is a hard reminder that the sea does not care what a brochure promises. The search for Titanic revealed ecosystems living on rust and metal. Decades after the ship sank, finding it required deep ocean technology, careful mapping, and patient searching across a vast seafloor. When explorers finally reached the wreck, the surprise was not only emotional. It was biological. The site was alive. Microbes and other organisms were feeding on the iron, creating formations that looked like underwater icicles of rust. The wreck had become a reef in the deep, a place where life gathered around a new source of chemistry. That discovery broadened public imagination. The deep sea was not an empty graveyard. It was a working ecosystem capable of colonizing even cold metal in darkness. The expedition also changed deep ocean exploration itself. Better cameras, better navigation, and better sampling methods grew out of the effort to locate and study the site without destroying it. Titanic became a bridge between history and ocean science, showing how a human tragedy can also become a laboratory for understanding life in extreme environments. Jacques Cousteau helped make underwater exploration a public fascination. Before Cousteau, much of the underwater world belonged to professionals, sailors, and divers with specialized access. He helped change that by showing the sea as a place ordinary people could wonder about, not just fear. Through films and television, audiences saw reefs, wrecks, and marine animals in motion, filmed from within the water rather than described from a deck. That shift mattered. When people can see, they care differently. Public fascination helped fund research, inspire future oceanographers, and build support for protecting marine environments. Cousteau also popularized the idea of the expedition ship as a moving studio where storytelling and investigation traveled together. The ocean became a stage for curiosity, not only for commerce or conflict. His legacy is complicated like all long careers, yet the impact is clear. Underwater exploration moved from rumor to shared experience. A world that was once hidden behind a surface shimmer entered living rooms, and it never fully left. The aqualung gave ordinary divers access to depths once reserved for professionals. For a long time, diving meant heavy suits, surface air hoses, and a narrow range of movement. The aqualung changed that by putting a breathing supply on the diver, freeing people to swim where they chose. Suddenly, exploration could be nimble. Divers could follow a reef wall, circle a wreck, or linger to observe animal behavior without being tethered to a boat by a long umbilical. That freedom helped create new kinds of work and new kinds of play. It also brought new responsibility because depth and time underwater carry real risks. Training, buddy systems, and careful planning became part of the culture, yet the transformation was profound. Underwater archaeology became more practical. Marine biology gained direct observation in natural settings. Photography and filmmaking underwater became accessible, and that shaped public understanding of the sea. The aqualung did not conquer the ocean, but it invited far more people to visit it and to return with stories that were personal and vivid. The first undersea habitats tested whether humans could live submerged for weeks. Living underwater is not the same as visiting. Undersea habitats were designed to answer a bold question. Can people stay below for long periods and still work effectively? Inside these sealed spaces, teams slept, ate, and planned dives while pressure outside pressed in and the surface felt far away. Saturation diving made it possible. When the body remains under pressure, divers can make repeated excursions without constant long decompressions. Though returning to the surface still requires time and careful control, the habitats became laboratories for physiology, engineering, and psychology. How does isolation feel when you can see sunlight through water but cannot touch air? How did teamwork and fatigue change when every exit demands a dive plan? These projects also advanced tools, communication systems, and life support methods that later helped research and industry. The results were not only scientific, they were human. They showed that exploration can become a way of living with routines and anxieties that feel like a space mission, except the ceiling is an ocean. Cold War submarines explored quietly and gathered hidden ocean data. During the Cold War, submarines were built for secrecy, deterrence, and surveillance, yet their missions often produced unexpected knowledge about the ocean itself. To navigate safely and remain hidden, crews needed detailed information about seafloor shape, temperature layers, and how sound traveled through different water masses. This pushed systematic mapping and careful measurement in places far from shipping lanes. The data was often classified, which meant the scientific world did not immediately benefit. But the work still advanced the practical understanding of underwater geography and acoustics. Submarines also traveled under ice and through deep basins that were difficult for surface ships to study in harsh conditions. The ocean became an arena where politics demanded precision and precision demanded observation. It is a strange chapter in expedition history. Curiosity was not the headline goal, yet exploration happened anyway. Driven by strategic necessity, the Cold War sent vessels into hidden corners, and those journeys expanded knowledge, even while they tried to remain unseen. Nuclear propulsion let vessels stay underwater longer than some wars lasted. Diesel submarines had to surface or snorkel regularly, which meant exposure, vulnerability, and limits on endurance. Nuclear propulsion changed the rules by allowing submarines to remain submerged for very long periods, limited mainly by food, maintenance, and crew. Stamina. This created a new kind of ocean presence. A vessel could cross entire basins without revealing itself, operate beneath ice, and maintain patrols that lasted far longer than earlier technology allowed. For expedition history, the importance is psychological as much as technical. The ocean became a continuous operating environment, rather than a place you periodically visited from the surface. Underwater navigation, internal life support, and crew routines had to be refined because the ship was now a sealed world for months. This capability also shaped global strategy in unsettling ways because hidden persistence changes deterrence and risk. Yet, it also indirectly expanded the human relationship with the deep ocean. Remaining submerged for so long forced better understanding of currents, sound channels, and seafloor obstacles, and it pushed engineering into a new era. The first global seafloor map exposed the mid-ocean ridge system. For centuries, maps treated the deep ocean as blank because nobody could see it. As soundings and later sonar surveys accumulated, a startling pattern emerged. A long mountain chain runs through the world's oceans, linking basins like a seam. This was the mid-ocean ridge system, a global feature that most people had never imagined could exist. Seeing it on a map changed the story of Earth. The seafloor was not static and flat. It had structure, continuity, and clues about processes beneath it. Mapping also revealed deep trenches, fracture zones, and broad plains, turning the ocean into a landscape with recognizable shapes rather than mystery. The creation of a global map required patience and collaboration with data drawn from many voyages and many instruments. It also required trust in indirect measurement because the mountain range was first known through echoes and numbers, not through human eyes. That shift matters. Expedition history often hinges on new ways of sensing. When the ridge system appeared, the ocean stopped being the edge of the world and became part of its engine. Plate tectonics was confirmed when expeditions read the magnetism of basalt. At sea, scientists began towing instruments that could sense tiny changes in Earth's magnetic field. What they found over the mid-ocean ridges was startlingly orderly. Bands of stronger and weaker magnetism ran alongside each other like stripes, and the pattern repeated in a mirrored way on both sides of the ridge. Rock on the seafloor had locked in magnetic direction when it cooled, and that direction matched the planet's field at the time. Since Earth's field flips occasionally, the stripes formed a timeline written into basalt. The symmetry implied motion, as if new seafloor was being created at the ridge and pushed outward. This was not a hunch from a desk. It was evidence gathered by ships crossing the same lines again and again, checking that the pattern held. When those stripes made sense, tectonics stopped being an argument and became a map of how Earth renews itself. Hydrothermal vents were discovered and rewrote ideas about life's limits. For a long time, it seemed obvious that life ultimately depends on sunlight. Deep ocean expeditions shattered that assumption when they found hydrothermal vents, places where heated water pours from the seafloor like an unseen spring. Around these vents, scientists saw dense communities of organisms thriving in darkness, supported by chemistry rather than photosynthesis. The energy came from reactions involving compounds in the vent fluids, and microbes formed the base of the food web. The discovery was dramatic because it changed two big stories at once. It changed what we thought the deep sea could host, and it changed what we thought life requires. The vents also suggested a new possibility for life beyond Earth, since other worlds might have dark oceans and internal heat. Ocean exploration suddenly felt like planetary exploration. A dive meant to study geology ended up expanding biology and imagination in one breath. Black smokers revealed minerals forming like chimneys built in fast motion. Some hydrothermal vents do not flow like a clear spring. They erupt as black smokers where superheated water loaded with minerals meets cold seawater and instantly precipitates a dark cloud. As particles fall, they build towering chimneys that can grow and collapse over surprisingly short time spans. Watching this is like watching a mountain build itself, not over ages, but within human attention. The chemistry is intense. Metals and sulfur compounds join in separating ways that leave layered deposits, and those deposits can form rich mineral structures on the seafloor. Expeditions that found black smokers realized they were seeing an active factory, one that turns Earth's internal heat into new materials in real time. The sights also create sharp contrasts. One step away from a vent can be near freezing, while the vent fluid can be hot enough to cook instantly. This is why the deep ocean can feel like science fiction while staying completely real. Ocean drilling cores turned mud into a climate timeline. When drilling ships pull long cylinders of sediment from the seafloor, they are bringing up time stacked in layers. Year after year, tiny shells, dust, ash, and organic fragments settle and compress, leaving a quiet archive that can stretch back millions of years. Scientists read these cores like a slow diary. Changes in microfossils show shifts in ocean temperature and chemistry. Variations in grain size can hint at stronger winds or different current patterns. Distinct ash layers can tie sediment to known eruptions, anchoring the timeline. What makes this so powerful is that the ocean collects signals from wide regions, not just one coastline. A core taken far from land can still record changes in ice, rain, and global circulation. In expedition history, drilling turned exploration into deep listening. The ship is not only traveling across space, it is sampling deep time. Mud becomes testimony, and climate becomes a story you can hold. The discovery of the deep scattering layer surprised navies and biologists alike. Early sonar operators noticed something strange. Signals bounced back from a broad layer in the water as if the seafloor had risen. Yet the depth changed from hour to hour. At first it looked like a phantom bottom, and it was unsettling for anyone relying on sonar for navigation or detection. The truth was even more fascinating. The layer was made of living creatures, many of them small that reflect sound. Even more astonishing was their daily movement. As daylight fades, they rise toward the surface to feed. When morning returns, they sink again into darker depths, forming a huge migrating band. This is one of the largest animal migrations on Earth, and it happens out of sight every day. The discovery linked military technology to biology in an unexpected way. It also reminded explorers that the ocean is not just water and rock. It has moving architecture made of life, and it can confuse your instruments until you learn its rhythms. The first CTD casts made temperature and salinity visible in profiles. A CTD package is lowered through the sea like a careful probe, measuring conductivity, temperature, and depth as it descends. What comes back is not a single number, but a vertical portrait of the ocean. Layers appear. Some are warm and mixed, some are cold and stable, and some mark sharp boundaries where density changes fast. Those boundaries matter because they shape how nutrients move, how sound travels, and how water masses circulate across basins. Before these casts, sailors could feel surface conditions and guess what lay below. CTD profiles turned guessing into structure. Scientists could compare stations across an expedition and watch the ocean change from place to place, not only across distance, but through depth. It also made oceanography more precise for future work, since the same instrument package could be used repeatedly with consistent method. A single cast can feel like lowering a question into darkness and bringing back a clear answer layer by layer. The Argo Float Network turned the ocean into a living data stream. Instead of measuring the ocean only where ships happen to travel, Argo floats measure it while drifting day after day across wide regions. Each float cycles through a simple routine. It sinks to a set depth, drifts with currents, then rises while recording temperature and salinity, and transmits the data before sinking again. The result is a global pulse of information collected in places and seasons where expedition ships rarely go. This changes how we understand the ocean's role in climate, because the sea stores vast amounts of heat and moves it around the planet. Argo makes that storage measurable at scale, not as a one-time snapshot, but as ongoing change. It also changes the feeling of exploration. The ocean is still immense, but it is no longer silent between voyages. The floats keep watching. They extend human curiosity beyond the horizon, and they do it patiently, thousands of times over. Satellite altimetry detects sea level changes by measuring tiny height shifts. From orbit, satellites can measure the height of the ocean surface with astonishing precision, and those small height differences reveal big stories. Sea level rises and falls with melting ice and warming water, but it also bulges and dips because currents and winds pile water up in some regions and draw it down in others. Altimetry turns those patterns into maps, showing features like eddies and boundary currents as changes in surface height. This is remarkable because it lets us see motion. Without watching a single wave, it also helps connect the surface to the deep. A raised sea surface can indicate warmer water below, while a depressed surface can signal colder, denser water. For expedition history, satellites represent a new era where exploration includes remote sensing, not only ships and nets. The ocean becomes measurable everywhere, including areas that are dangerous, remote, or politically hard to access. It is a new kind of voyage where the instrument circles the planet and reads the sea in fine detail. Remote islands were claimed by planting flags, then contested for centuries. In many eras, arriving first was treated like ownership. Crews would land, raise a flag, read a declaration, and record the act in a log book as if the ocean had delivered empty space meant to be taken. The reality was often more complicated. Some islands were inhabited and claims ignored existing lives. Other islands were uninhabited, but still mattered because they offered fresh water, safe anchorages, or later a base for refueling and communication. Over time, those scraps of land became points of argument, pulled into rival maps, treaties, and disputes. A speck in the sea could gain value as technology changed. A place that mattered only to a passing sailor could later matter for cables, air routes, or exclusive economic zones. This is why ocean expeditions are tied to politics as well as curiosity. The moment of arrival can echo for generations, and a simple flag can start a long argument about who belongs where. The race to measure Earth's shape depended on long sea voyages. To understand Earth's true shape, scientists needed measurements taken far apart across different latitudes. That required travel, not just calculation. Instruments had to be carried carefully. Observations had to be repeated, and results had to be brought home for comparison. Ocean voyages made that possible by connecting distant points with a practical route. Even when overland travel was slow or dangerous, ships transported survey teams, clocks, telescopes, and notebooks to places where the sky could be observed and where baseline distances could be measured. The goal was not only curiosity, better knowledge of Earth's size and shape, improved maps, navigation, and the accuracy of positions at sea. This is a beautiful loop. Expeditions used navigation to gather measurements, and those measurements improved navigation for later expeditions. The sea helped turn a planet into a quantified object, not as an abstract idea, but as something humans could measure with patience, travel, and repeatedly. Observation. Coral reef expeditions showed reefs grow slowly, yet can vanish quickly. Coral reefs can look as permanent as stone, yet expeditions revealed a different truth. Much of a reef is built by countless tiny animals laying down skeletons millimeter by millimeter, season after season. That slow construction can take centuries to create the architecture that protects coastlines and shelters fish. Then a heat wave, pollution surge, or violent storm can damage that structure in a single season. Researchers who revisit the same reef sites across years see this contrast with painful clarity. A reef can be a thriving city of color and sound, then become a pale, brittle place that struggles to recover. That discovery changed how people think about time in nature. The ocean can build patiently, and it can also undo quickly. Reef expeditions also taught a wider lesson about stewardship. If something takes so long to form, then losing it is not just a momentary setback. It is the disappearance of history that cannot be replaced on a human schedule. Mapping the Great Barrier Reef required years of patient surveying. The Great Barrier Reef is not one neat line on a map. It is a sprawling maze of reefs, shoals, channels, and sudden shallows that can punish a ship that trusts the wrong chart. Surveying it demanded repeated passes, careful soundings, and the humility to return and correct what earlier work missed. Crews had to read watercolor, watch wave breaks, and measure depth again and again, while weather and tide tried to scramble the results. The patience was not academic. Accurate maps meant safer navigation for everyone who followed, from coastal traders to research vessels. The work also revealed how complex reef systems are. They shift, grow, erode, and scatter hazards across wide areas that look calm from a distance. Charting such a place is like drawing a living labyrinth. The accomplishment was not a single dramatic moment. It was persistence layered over years, turning risk into knowledge, one careful measurement at a time. The Galapagos became a laboratory, reached only by hard sea travel. Reaching the Galapagos used to mean committing to long days of open water with uncertain winds and limited resupply. That isolation is exactly what made the island so scientifically powerful. They functioned like a set of natural experiments, where similar creatures could diverge on different islands under different conditions. Expeditions brought observers who compared patterns, asked uncomfortable questions, and carried those questions back to the wider world. The islands also forced people to look closely. When you are far from home, every detail matters. Shorelines, food sources, and wildlife behavior become more than curiosities. They become information that might decide your success. Over time, the Galapagos earned a reputation as a place where big ideas can start from small observations. A finch beak, a lizard's habits, a plant's distribution. The sea journey was part of the lesson. Isolation can concentrate insight. Distance can sharpen attention. An archipelago reached by effort can return knowledge that travels everywhere. The Krakatoa eruption was recorded by ships that felt the shock waves. When Krakatoa erupted, the event was not contained by geography. Ships at sea became witnesses, not by choice, but because the ocean carried the disturbance outward. Mariners reported thunderous sounds, strange darkness, and waves that did not behave like ordinary storms. Some crews felt pressure changes, and some encountered floating pumice that turned water into a gritty, unstable surface. The sea itself became a messenger transmitting tsunamis across wide distances and making coastlines far away part of the disaster. These shipboard observations mattered because they captured timing, direction, and scale in places without land-based instruments. They also showed how interconnected ocean hazards are. A volcano can reach into shipping routes, harbors, and distant shores through the medium of water. For expedition history, this is a reminder that the sea is not only a route. It is a system that moves energy as well as ships. When Earth reshapes itself, the ocean helps spread the news, sometimes before any official report can. The first global ocean census began as thousands of separate voyages. No single ship can catalog the ocean's life because the sea is too large and too varied. A global census had to be assembled like a quilt with thousands of voyages, collecting samples, recording sightings, tagging animals, and comparing habitats across years. Each expedition added a few tiles to a mosaic that slowly became recognizable. Researchers learned where biodiversity concentrates, where migrations pass, and how ecosystems differ between coasts, open water, and deep zones. The work also exposed how much was missing. Many species were unknown, many regions were undersampled, and many patterns changed with season and climate. That is what makes the effort so captivating. It turns exploration into collaboration across oceans and generations. The census was not only about naming creatures, it was about understanding relationships, abundance, and change. When you count life in the sea, you also begin to notice what is disappearing. A census can feel like celebration and like a warning. At the same time, the Terra Oceans project sampled plankton, then rewrote marine family trees. Plankton can be microscopic, yet they steer the ocean's food webs and influence the air above the sea. The Terra Oceans Project treated these tiny drifters as worthy of a grand expedition, collecting samples across many regions and conditions. By analyzing genetic material, researchers found surprising diversity and unexpected connections between organisms that look similar but are not quite as closely related. In some cases, the results reshaped how scientists classify life in the ocean because genetics revealed hidden branches that traditional observation could not. The expedition also highlighted how plankton communities shift with temperature, nutrients, and currents, making them sensitive indicators of environmental change. What feels mind-bending is scale. A jar of seawater can contain an entire universe of interactions, predators, prey, parasites, and partners. By sampling that universe systematically, Tara Oceans helped reveal a living network that supports fisheries, carbon cycling, and ocean health. It is expedition history at its most modern. Sail across the world, then discover that the biggest revelations can be smaller than a grain of sand. Ocean expeditions found plastic in trenches once thought untouched. For a long time, the deepest trenches were treated as remote, protected by sheer difficulty. Getting there requires specialized vessels and careful planning, so it was tempting to imagine those places as clean by default. Expeditions shattered that comfort by finding plastic debris and microplastics even in the Hadal zone. The discovery is not only depressing, it is revealing. It shows how ocean currents, sinking particles, and food webs can carry human material into the most isolated environments on Earth. It also reframes pollution as a three-dimensional problem. Plastic does not stay near shore, and it does not stay near the surface. It travels, fragments, and enters ecosystems that are slow to recover from disturbance. When scientists pull samples from extreme depths and find traces of everyday packaging, it changes the emotional scale of responsibility. The ocean can hide things from our eyes, but it cannot shield itself from our habits. A trench that once symbolized mystery now also symbolizes reach, the reach of human impact into darkness. The search for MH370 became one of the largest scans ever. When Malaysia Airlines flight MH370 disappeared, the ocean became a vast investigation scene with almost no obvious clues. Search teams had to combine satellite data, drift modeling, sonar mapping, and deep-sea surveying across enormous areas. The scale of the effort was staggering, not because ships were chasing a visible target, but because they were trying to find a needle in a seafloor that looks endless. Each new search pass produced maps of underwater terrain that had never been charted in such detail, turning tragedy into exploration. The work also exposed how hard the deep ocean is to search, even with modern technology. Weather limits operations, equipment can fail, and interpretation is difficult when every echo could be rock, debris, or nothing. The search became a lesson in patience and uncertainty, and it showed how the ocean can still keep secrets in an era of satellites. It also showed how much humanity will invest in answers, even when the sea offers silence. Modern ROVs work in darkness for hours, guided from a bright ship. A remotely operated vehicle can descend miles into black water, where pressure crushes and human lungs cannot function. It carries cameras, lights, arms, and sensors, then sends it to you back through a tether to a ship on the surface. This creates a strange, split reality. On deck, people stand in bright air, watching monitors, while the machine moves through cold darkness where the only light comes from its own lamps. ROV pilots learn to maneuver delicately because a wrong move can stir sediment into a blinding cloud or damage fragile life. With robotic arms, they can pick up rocks, collect organisms, or inspect wrecks with precision that early expeditions could not dream of. These live feeds also change who can participate. Scientists, students, and the public can watch discoveries live without going to sea themselves. That immediacy reshapes exploration culture. The deep becomes less distant when you can see it in real time. Yet the ocean remains demanding because every hour down there depends on engineering, teamwork, and respect for an environment that punishes mistakes. Autonomous gliders cross basins silently like slow underwater kites. An ocean glider does not roar through water with propellers, it slides. By changing buoyancy, it rises and falls, converting that vertical motion into forward movement with wings. The result is slow, efficient travel that can last for weeks or months, covering long distances while collecting data. Gliders measure temperature, salinity, oxygen, and other signals, building a moving picture of conditions across seasons and storms. Because they are quiet, they can also study areas where noise would disturb marine life or interfere with acoustics. They extend expedition reach into places too dangerous or expensive for ships to patrol continuously. What is captivating is their patience. A glider can keep going when humans would need rest, and it can watch gradual changes that a short cruise would miss. This is a new kind of ocean expedition, one where exploration is delegated to a persistent machine that drifts, dives, reports, and keeps learning. It feels less like conquest and more like listening over time. The first women oceanographers fought for berths, then changed the science. They faced barriers that sound absurd now, yet they were real. Some were told ships had no space for them, or that their presence would distract crews, or that a woman on board was unlucky. Even when they earned degrees and published papers, access to research vessels could still be blocked by tradition rather than merit. So many built alternate paths. They analyzed samples brought back by others, ran laboratories on shore, and fought for policy changes that opened sea time to more researchers. When opportunities finally cracked open, they did not arrive as visitors. They arrived with questions that reshaped fields. From plankton ecology to chemical oceanography to mapping and climate work, their story matters because expedition history is not only about oceans. It is also about who is allowed to ask the ocean questions. Once more voices reached the deck, the science got bigger, sharper, and far more human. Marie Tharp's maps revealed ridges and rifts despite decades of doubt. She worked with sounding data that looked like scattered numbers to many people, then turned those numbers into a coherent seafloor landscape. As she traced profiles across the Atlantic, a persistent feature began to appear, a ridge with a central valley running down its length. The idea that the seafloor had a continuous rift was hard for many to accept, and her interpretation was often dismissed before it was evaluated. Still, she kept drawing, cross-checking, and refining. When her maps were paired with other evidence, they helped make the case that the ocean floor was dynamic, not static. What makes her story so gripping is that the discovery was not a single dramatic dive. It was pattern recognition, patience, and confidence in what the data kept saying. Her work shows that exploration can happen at a desk with a pencil and relentless integrity, and it can still change how humanity imagines Earth. Indigenous wayfinding survived colonization and is now being taught again. For many ocean cultures, navigation was never only a technical skill. It was identity, inheritance, and community memory. Colonization disrupted that chain, replacing local knowledge with imposed routes and imported instruments. And in many places it tried to frame ancestral wayfinding methods as superstition. Yet wayfinding endured. It survived in stories, in practice, and in people who refused to let it disappear. In recent decades, revival voyages and training programs have brought this knowledge back into public view, with students learning to read star paths, swells, and winds through direct experience. These journeys are not reenactments for show. They are proofs of competence and acts of cultural restoration. They also expand how we define science. Observation, repetition, and apprenticeship are scientific habits, even when they live outside universities. The revival reminds us that the ocean has always been known in more than one way, and that recovering those ways can be a form of healing. Lighthouse networks grew because one hidden reef could ruin a fleet. Before modern navigation aids, a coastline could be a trap that waited in silence. Reefs, shoals, and shifting sandbars could sit just below the surface, invisible until surf broke or wood cracked. Lighthouses became answers to that fear. Not just single towers, but networks designed to guide ships through approaches, mark hazards, and create recognizable patterns at night. Each light was a promise, telling sailors there was a fixed point in a world that moved. Building them was difficult and dangerous. Some were raised on wave-battered rocks where construction crews had to fight weather as much as engineering. Their impact reached beyond safety. Reliable coastal navigation improved trade, reduced insurance risk, and helped ports grow. Lighthouses also shaped expedition confidence. When a ship returned after months away, a familiar light could be the first sign of home. These towers are often treated as romantic symbols, yet their real history is practical and urgent. They were built because the sea collects mistakes and because people refuse to accept loss as inevitable. Maritime quarantine stations shaped health policy long before germ theory was common. Ports were gateways, and that meant they were also vulnerable. A ship could bring cargo and wealth, but it could also bring illness that spread through crowded streets faster than any sailor could describe it. Quarantine stations emerged as defensive infrastructure. Ships were held offshore, passengers were inspected, and goods were aired, washed, or destroyed, all based on evolving ideas about contagion and risk. Even when people lacked modern explanations, they could see patterns. Outbreaks followed arrivals, isolation reduced spread. These stations were often tense places filled with uncertainty, fear, and conflict between public safety and commerce. They also created early versions of public health administration. Who has authority to detain a ship? How long is long enough? What evidence is needed? Ocean travel forced societies to build rules for invisible threats. In expedition history, quarantine is a reminder that exploration connects bodies as well as maps, and that every new route can carry passengers. Shipboard astronomy made observatories portable and sharpened timekeeping standards. A clear night at sea can be astonishing, and for navigators, it was also a workplace. Astronomical observations helped determine position, calibrate instruments, and check the accuracy of clocks that crews depended on. Ships carried sextants, telescopes, and tables, turning decks into moving observatories that had to work despite rolling wind and spray. The effort pushed precision forward. Crews learned to standardize procedures, record results consistently, and compare readings across voyages. Ports and navies demanded better chronometers, better tables, and better training, because a small error in a star sight could become a large error on a reef-strewn tower coast. In this way, ocean expeditions strengthened the partnership between astronomy and practical navigation. The sky was not just beautiful, it was a reference system. When thousands of sailors relied on the same celestial methods, timekeeping itself became more disciplined and more universal. The ocean helped drive standards that later supported everything, from global mapping to reliable schedules. The Beaufort scale began as a practical language for describing wind. Wind is hard to measure with words when people use different meanings for the same feeling. The Beaufort scale changed that by linking wind force to observable effects, so a report could be understood without instruments. Instead of vague descriptions, sailors could describe conditions by what they did to the sea and to a ship's sails. That created shared language across navies and merchant fleets, and it improved decision-making. A captain reading a forecast or a log entry could picture the conditions more clearly, and planners could compare routes and seasons with less confusion. The scale also made experience transmissible. A new sailor could learn what Force 6 means by watching the ocean's behavior, then carry that understanding to any coastline. Over time, the Beaufort scale became part of modern meteorology, yet its roots are intensely human. It came from the need to communicate danger quickly and reliably, when a misunderstood wind could cost a mast, a cargo, or a life. Sea shanties synchronized labor and carried news across oceans. On a sailing ship, many tasks demand perfect timing. Hauling a heavy line, raising a yard, or turning a capstan goes better when bodies move together, not in scattered effort. Sea shanties were work tools built from rhythm. A leader would call, the crew would answer, and the shared pulse kept everyone pulling at the same moment. That coordination reduced injury and increased efficiency, which is why the song spread. They also carried culture. Verses changed with ports, crews, and events. So a song could become a moving bulletin board, carrying gossip, grief, and humor from harbor to harbor. In a world where news traveled slowly, sailors often arrived with stories before official letters did, and songs helped preserve those stories in memorable form. Shanties remind us that expedition history lives in muscles and voices, not only in documents. The ocean demanded labor, and labor created music that still echoes today. The first global weather charts were built from scattered expedition logs. Long before computers, a global view of weather had to be assembled by hand from countless local observations. Ship logs recorded winds, pressure, cloud cover, and storms in places where no land station existed. When these records were gathered and compared, patterns began to emerge across oceans, seasons, and latitudes. Scientists and forecasters could identify prevailing wind belts, storm tracks, and regions of frequent calm. This knowledge improved route planning and reduced risk because captains could anticipate the kinds of weather they might meet, even if they could not predict the exact day. The creation of weather charts also marks a shift in mindset. Individual experiences became a shared data set. A storm that terrified one crew became a point on a map that could help another crew avoid the same fate. In expedition history, these charts are evidence of collective learning. The ocean taught, ships recorded, and society slowly learned to read the sky with more confidence. Ocean expeditions often returned with maps and with new words for the world. When people encounter unfamiliar landscapes, animals, tools, and customs, language has to stretch. Expeditions brought home more than coordinates. They brought names, loanwords, and new meanings for old terms. Sometimes explorers adopted local words because their own languages had no precise match. Sometimes they invented labels that stuck, even if they were clumsy or biased. Words entered dictionaries through journals, trade, and conversation in port cities where cultures mixed daily. The process shaped how distant places were imagined by those who never traveled. A name can carry awe, misunderstanding, or power, and it can influence policies and attitudes for generations. This is why vocabulary matters in expedition history. Language is not neutral packaging, it is part of the legacy. A coastline mapped and named becomes easier to discuss, easier to claim, and easier to mythologize. Expeditions expanded the world, and they expanded the words people used to hold that world in mind. The deepest trenches were named before anyone could actually see them. For a long time, the deepest places in the ocean were known only through inference and patience. Expeditions dropped sounding lines and later used echo measurements, then compared results across many crossings to locate the most extreme depths. Names were assigned to features that no human eye had ever witnessed directly, which is a wonderfully bold thing to do. It is like naming a mountain you have never seen, based only on how far your measurement keeps falling. Those names carried stories and rivalries. They marked achievements, honored ships, and claimed a kind of intellectual ownership over the unknown. Only much later did cameras and deep-diving vehicles confirm what those measurements suggested. The sequence matters. In ocean history, knowledge often arrives first as numbers and maps. Sight comes later. The trenches were real before they were visible. And that gap between knowing and seeing is one of exploration's most fascinating tensions. Early expedition sketches served as biology textbooks for landlocked scientists before photographs could travel easily. A careful drawing could be the difference between knowledge and rumor. Artists on expeditions sketched fish, birds, shells, and sea plants with an urgency that mixed wonder with responsibility. A scientist back home might never see a living coral or a strange deep water catch. Yet a drawing could preserve shape, proportion, and key features well enough for study. These images became a kind of portable fieldwork passed between libraries and lecture halls as evidence from faraway water. The best expedition artists learned to capture detail without turning animals into fantasy, and they worked quickly because specimens decayed and colors faded. Sketches also preserved context. A shoreline profile could show where a creature was found, and a scene of a reef could show life clustered together. This is how the ocean entered scholarship for people who never left shore. Pencil lines became stepping stones across distance. Sea ice charts saved ships and became early climate archives. In polar waters, sea ice is not background scenery. It is a moving hazard that can trap, crush, or block a route entirely. Explorers began recording ice edges, leads, and the timing of freeze and breakup because a single wrong assumption could end a voyage. Those charts were practical tools shared between captains who understood that memory alone was not enough. Over years and decades, the records became something else as well. They formed an unintended archive of changing conditions. When later researchers compared old charts with newer observations, they could see shifts in timing and extent that hinted at broader climate patterns. What began as a survival document became evidence. This is a common theme in expedition history. People write down what they must, then future generations read those notes as more than logistics. The ice charts show the ocean as both threat and witness, and they remind us that data can outlive the crisis that produced it. The first circumnavigations changed diets, languages, and trade in every port. A circumnavigation was not just a line around a globe. It was a moving exchange that reshaped daily life wherever ships stopped. Crews carried food preferences, cooking techniques, and cravings, then encountered ingredients and tastes that were entirely new to them. Spices, preserved goods, and unfamiliar fruits entered diets, sometimes as luxuries, sometimes as necessities that kept sickness away. Languages changed too. Sailors picked up working phrases, insults, jokes, and bargaining words, then carried them onward like stowaways in the mouth. Trade followed the same pattern. A port that gained a reputation for supplies or repairs could become part of a repeating circuit, and that circuit altered local economies. Yet the exchange was never equal. Power often traveled with cannons and contracts, and some goods were taken through coercion. Still, the cultural shift is undeniable. When ships began circling the world, they also began mixing the world, one harbor at a time. Shipboard clocks standardized time zones long before radio time signals. Before instant communication, time was surprisingly local. Noon was when the sun reached its highest point, and that was enough for many towns. Ocean travel forced a different discipline. Navigators needed reliable timekeeping to compare positions and keep schedules across long distances. On ships, clocks, and chronometers became authorities that everyone obeyed, from the officer taking observations to the crew changing watches. As voyages linked distant ports more regularly, the need for shared time grew. Shipping timetables, port operations, and later rail connections all benefited from agreement about what time it was meant to be. Shipboard practice helped push that agreement forward because sailors lived by standardized routines while traveling through changing longitudes. The day itself could feel strange on the long voyage, counted carefully. It did not always match the calendar you expected when you returned. This pressure to coordinate time laid groundwork for broader standardization even before radio signals could broadcast unofficial moment across oceans. Antarctic soundings showed continental shelves, hide valleys carved by ancient ice. When expeditions began measuring depths around Antarctica, they found that the shallow margins were not smooth ramps into the deep. Soundings revealed complex shapes, including broad troughs that cut into the continental shelf. These hidden valleys suggested a powerful past. Ice sheets can act like slow-moving bulldozers, grinding and carving the seafloor when they extend outward. The idea that ancient ice could reshape not only land but also submerged terrain made Antarctica feel more dynamic even in its apparent stillness. For explorers, the discovery added new stakes to mapping. A shelf that looks uniform on a small scale can hide features that affect currents, sea ice movement, and the behavior of glaciers today. Soundings were also acts of courage. Working near the Antarctic coasts means dealing with sudden weather and drifting ice while trying to take measurements that demand steadiness and repetition. Each depth reading helped reveal a story of ice that once reached farther and a seafloor that still remembers it. The discovery of manganese nodules hinted at slow geology on abyssal plains. When expeditions hauled samples from deep flat seafloor, they sometimes found strange rounded lumps scattered across the sediment. These manganese nodules looked almost ordinary, like stones you might pick up on a beach. Yet they formed in a way that is anything but ordinary. In the abyss, where sediment can fall slowly, minerals can accumulate around a small core over extremely long spans of time. Each nodule is a quiet record of chemistry and patience, built by processes that do not need earthquakes or volcanoes to make progress. Their discovery changed how people imagine the abyss. The abyss was not a featureless void. It was a landscape where subtle processes could build tangible objects, even in near darkness and high pressure. The nodules also sparked debates about resource extraction, because a slow-grown object can become a fast-removed commodity. Expeditions brought them up as curiosities. Then the world began asking what it would mean to take them. Expeditions that hunted sea monsters often found squid and kept wondering. Sailors have always told stories of enormous shapes in the water, and some expeditions set out hoping to prove or disprove them. When nets came up with massive squid, the line between legend and biology blurred in an exciting way. A giant squid is not a dragon, yet it is large enough, strange enough, and powerful enough to explain why people once spoke of tentacle terrors. These animals live in deep water where human eyes rarely go, which means most encounters happen by accident. A squid might wash ashore, be found in a stomach, or appear briefly near a ship, then vanish. Expeditions collected beaks, scars, and occasional specimens, then argued about size and behavior with limited evidence. The hunt for monsters did not end in embarrassment. It ended in a better question. If creatures this dramatic can live unseen, what else lives beyond our routine reach? The monster stories became a gateway into real deep-sea mystery. Marine archaeology now finds ancient harbors. Underwater, proving coasts have moved. Sometimes the ocean keeps history better than the land does. Underwater surveys have revealed submerged walls, anchors, and harbor structures that once sat in busy coastal zones. Their presence underwater is a reminder that shorelines are not fixed. Sea level can rise, land can sink, and storms can reshape coasts, leaving human infrastructure stranded below the waves. Finding an ancient harbor is like finding a city street in a place where fish now swim. It forces a different view of the past. People did not always live where modern maps suggest, and trade networks once touched places that are now submerged. Marine archaeology also demands careful technique. Currents, low visibility, and fragile materials mean a site can be damaged easily by careless hands. The best expeditions treat these locations as archives, not treasure piles. Each artifact is a clue about commerce, daily life, and technology, and the surrounding seabed can hold context that land excavations often lose. The ocean becomes not only a subject of exploration, but also a curator of human memory. Every new ocean map still begins with the same act, sending a line down. Modern ships can paint the seafloor with multi-beam systems and sophisticated sensors. Yet, the heart of the task is still a question asked in the oldest possible way. How deep is it right here? The earliest answer was a weighted line lowered until it touched bottom. That act created the first honest contact between a ship and the unseen world beneath it. It also created a discipline of verification. A map is not imagination. It is measurement repeated until it agrees with itself. Even now, calibration and ground truth matter. Instruments are checked, readings are compared, and the ocean is sampled directly to confirm what remote sensing suggests. The romance of exploration often focuses on distant horizons, but this is the quieter truth. New knowledge often starts with a single point measured carefully. Drop the line, record the depth, do it again somewhere else. Oceans become charts through countless small acts of attention, and the tradition links today's expeditions to the earliest ones. As we come to the end of our journey, You might notice how wide the ocean feels now, not just as water, but as history. We sailed with early navigators who trusted stars, wind, and memory. We followed empires that treated sea routes like arteries carrying food, language, and power from port to port. We watched instruments turn uncertainty into coordinates, and we felt how a single invention could make whole horizons reachable. We drifted into the polar margins where ice does not negotiate and where survival depended on patience, teamwork, and knowledge. Burned the hard way, we dove into the deep where the seafloor revealed ridges, trenches, and strange life that thrives without sunlight. And we saw how modern expeditions still chase mysteries from missing wrecks to hidden ecosystems, while the ocean quietly keeps its own pace. If you are still awake and you would like another slow voyage through the past, there will be a next video waiting for you on the screen. You can simply let it play and keep following the thread of discovery wherever it leads. But for now, you do not need to navigate anything at all. Let your jaw unclench, let your shoulders drop. Feel your breathing find an easier rhythm in and out like a tide that knows exactly where it belongs. Imagine the last light fading behind a quiet horizon and a steady ship moving forward without effort. Sleep well and good night.